Now we want to look at our f of xy equals x over y function as we can illuminate its graph in 3 dimensions. First of all, and we want to look at specifically what happens to the function near the point 2, 3, where x equals 2, y equals 3. If we first confine ourselves to the x equals 2 plane, then we find that z, which is equal to f of xy, is equal to 2 over y. So we have z versus y. Z is 2 over y. And that's going to give us just a hyperbola in the way that you should understand very thoroughly. At the point where y equals 3, we find that, well, z equals 2 over y. Z is going to equal 2/3. So we have the point 3, 2/3 on the graph. So we could even label that. I've got room. So there's our point 3, 2/3 on the graph of the YZ plane that we get when x equals 2. This is not the YZ plane of our three-dimensional coordinate system. It's the plane parallel to that YZ plane where x equals 2. We can see very clearly that the slope at this point is what? Okay, well, take the derivative. The derivative of 2 over y with respect to y, because y is changing, is negative 2 over y squared. So the slope when y equals 3 is negative 2 over 3 squared, which is negative 2/9. So now we have slope negative 2/9, and we can actually get then a vector in this direction. Okay? The vector in this direction that we're going to choose is, well, if the slope is negative 2/9 and we do a run of 1 corresponding to a displacement in the direction of the j vector, a displacement of magnitude 1, then the rise, which is going to be in the direction of the z vector or the k direction, is going to have to be negative 2/9 in order for rise divided by run to equal negative 2/9. Remember, the run is 1. So if the rise over the run is going to equal negative 2/9 and the run is 1, the rise had better be negative 2/9. This motivates the vector j, 1 unit in the y direction, minus 2k, or minus 2/9 k, 2/9 of a unit in the perpendicular direction, the direction of the rise on this graph. So this vector is going to be tangent not just to this curve, but to the entire surface. Okay, it'll be confined to the x equals 2 plane, as it is because you have no I component. But it's still going to be tangent to the plane. And you can think of how this relates to the woodblock picture. Okay, if we confine ourselves to the y equals 3 plane, and why would we do that? Well, we're looking at this thing near the point 2, 3. So let's write that out. We're looking at the point, at the behavior of the function near 2, 3. Well, at the point 2, 3, the x equals 2 plane, the x equals 2 plane is going to intersect the y equals 3 plane. X equals 2 intersects y equals 3 when x equals 2 and y equals 3. So, confining ourselves to the y equals 3 plane, well, if y is 3, then our function is just x over 3. So we have z equals x over 3. Now that's very simple. That's just a straight line with a slope of 1/3. We don't even need to take a partial derivative, although we can. The slope anywhere in this plane, though, will be the slope of this line, which will be 1/3. So we're going to have a tangent vector. And this is a vector not just tangent to this line, but tangent, again, to the surface. And that tangent vector will be I plus 1/3 k. Now, the vector j minus 2/9 k can be represented as j plus the partial of f with respect to y at the point 2, 3 times k. The partial of this function with respect to y treat x as a constant, you get negative x over y squared. Plug in the coordinates 2, 3, you get negative 2 over 3 squared, which is negative 2/9. So this is just the partial derivative of the function with respect to y, and if you understand where the partial derivatives comes from, they can be understood as confine yourself to a plane where x is constant, take the derivative of the function you get, and where x is equal to whatever number goes in here, of course. You have a mechanism for calculating a tangent vector, and you do the same here. The partial of f with respect to x at the point 2, 3, well, the partial of this function with respect to x is just 1 over y. Treat y as a constant, x is your variable. Derivative of x is 1, you get 1 over y. And then you plug in the x coordinate 2, but the derivative has no x value in this case. And the y coordinate 3, you get 1 over 3. Okay, so we get this vector, we get this vector. Here's a picture of the vector in its respective plane, and here's a vector in its respective plane. So how do we put that together into a picture of the behavior of the function near the point where x equals 2, y equals 3? We'll get that in another video.